Welcome back to The Explainer. Today, we are going to crack a problem that, trust me, shows up all the time in tech interviews. It's an absolute classic for getting your head around dynamic programming, the longest common substring. Okay, let's just dive right in. So if you've ever had that little moment of panic when an interviewer says, all right, let's talk about strings and dynamic programming, then you are in exactly the right place. By the end of this, you're going to feel so much more confident and ready to just tackle it head on. We're going to break it all down into 6 parts. We'll define the challenge, talk about a common trap to avoid, have that aha moment with DP, see it visually, write the code, and then get you prepped for those tricky follow-up questions. So first things first, let's make sure we're all 100% clear on what the problem is even asking for. Okay, the official definition is this. Given 2 strings, S1 and S2, find the length of the longest substring that shows up in both of them. And the keywords here are length and substring. We're not looking for the string itself, just its length. That's our answer. Now, this right here is probably the #1 thing that trips people up. Substring versus subsequence. They sound similar, but they are not the same at all. A substring has to be a continuous, unbroken block. See here? BCD is a substring because all those letters are right next to each other inside A, B, C, D, E, F. A subsequence, on the other hand, can have gaps. The order still matters, but you can skip letters. So ADF is a subsequence, but it is absolutely not a substring. For our problem today, we only care about those solid, contiguous blocks. Let's make this super concrete with an example. Say we have string 1, ABCDFE, and string 2, ZBCDFE. What's the longest continuous chunk they have in common? Well, it's BCDF. And how long is that? It's 4 characters. So 4 is our answer. Simple as that. All right, when you first see this problem, your brain probably jumps to a really direct, simple solution. And you know what? That's a great place to start in an interview. But it's often a trap if you just stop there. The brute force way of thinking is pretty straightforward, right? You just generate every single possible substring from the first string. Then, for each one of those, you check if it's hiding somewhere inside the second string. All the while, you just keep track of the longest one you found so far. And look, for tiny strings, this totally works. But an interviewer is always going to ask about efficiency. And this approach, it's really slow. The time complexity is just way too high for a typical coding challenge. It's not going to fly. We need a smarter way. And this is where we get to the really elegant solution, dynamic programming. Now, don't let the name scare you. It's not some crazy algorithm. Just think of it as a clever trick to use memory so we don't have to do the same work over and over again. The whole solution really boils down to this one simple idea. If we're comparing 2 characters and they match, we know that the common substring we just found is exactly 1 character longer than the one that ended at the position right before it. It's like we're extending a chain. And if the characters don't match, the chain breaks. We start over from 0. You know, this idea is so much easier to grasp when you can actually see it. So let's build out a DP table, just like you would on a whiteboard during an interview. Let's visualize this thing. Okay, so we set up a simple 2D grid. We put 1 string along the top and the other one down the side. Now, every single cell in this grid is going to represent a subproblem. It's going to store the length of the common substring that ends right at that specific character combination. So, as we fill this table out, the rule is dead simple. For every cell, we just ask, do the characters for this row and column match? If they do, we look at the number diagonally up and to the left, and we just add 1 to it. We're extending that chain. If they don't match, the chain's broken. We put a 0. And here's the final table, all filled in. Check out the cell where the C from S2 and the C from S1 meet. It has a 2. Why? Because C matches C, and the value in the diagonal cell for B and B was 1. So we just did 1 plus 1. And you can actually see this beautiful diagonal line of increasing numbers, 1, 2, 3, and finally 4. That represents our growing substring BCDF. So here's the best part. While we're filling out this table, all we have to do is keep another variable on the side that tracks the biggest number we've seen so far. In this case, the largest value we write down anywhere is 4. And that single highest value is our answer. That's it. Now that we've got the visual logic down pat, turning this into code is actually surprisingly straightforward. That table we just drew, it becomes a 2D array. And filling it out, that just becomes a nested loop. And here's what it looks like. The code is a direct translation of what we did on the table. We set up a DP table, usually filled with zeros to start. Then we have nested for loops to go through every single cell.
Inside, there's a simple if statement. Do the characters match? If they do, we set the current cell to be 1 plus whatever is in the diagonal cell. And the whole time, we're just updating a variable to keep track of the max length we've found.
Just finding the length is great, but a really sharp interviewer is going to push you a little further. And getting these follow-up questions right, that's what separates a good answer from a great one.
Okay, first, complexity. Time is O of m times n. Why? Because we have to visit every cell in that grid exactly once. Makes sense, right? Space is also O of m times n because we built that whole grid. But, and this is a fantastic bonus point to mention, you can optimize the space down to O of the minimum of m or n because you only ever need the previous row to calculate the current one. Finally, be ready to explain the difference with longest common subsequence. With Subsequence, if characters don't match, you don't just put a 0. Instead, you carry over the maximum from either the cell above or the cell to the left. It's a key difference.
And for the final challenge I'll leave you with, this is a classic follow-up. You found the length, it's 4. But how would you change your code to actually return the string BCDF itself? Think about where that 4 is in the table and how you might be able to work backward from there to rebuild the string.
And there you have it. That's how you really crack the longest common substring problem. If this was helpful, please hit that subscribe button for more deep dives into classic interview questions. The full commented Python code is up on our GitHub, and the link is right there in the description. Thanks for watching.